The fundamental objective of Bayesian data analysis is to determine the posterior distribution p theta by x, and the computational issue is the difficulty of evaluating the integral in the denominator, px. There are several ways of calculating the integral of the denominator. These include Monte Carlo methods, of which the most famous is the Markov chain Monte Carlo method. These methods are based on constructing a Markov chain that has the desired distribution as its equilibrium distribution. The state of the chain after a number of steps is then used as a sample of the desired distribution. The quality of the sample improves as a function of the number of steps. In this context, we, as part of the Stanford Scholar Initiative, will present this publication, Ensuring Rapid Mixing and Low Bias for Asynchronous Gibbs Sampling by authors Disa, Olukotun and Ray in relation to the asynchronous Gibbs sampling. First, what is the problem we are facing? Discrete graphical models are the center of Gibbs sampling applications. Its uses are very broad, from web information extraction to the vast field of image processing. The size and complexity of the databases used leaves the word huge small. For sparse graph, Gibbs sampling is broadly applied, running fast on modern hardware that is moving towards parallel architecture. We should leverage this to make Gibbs sampling more efficient and closer to real-world data. The loop in the algorithm isn't inherently serializable, thus doesn't get faster when run on parallel architecture. The hog-wild sampling, also known as asynchronous sampling, tries to resolve this issue. The problem is broken down into roadblocks that need to be overcome, namely bias and mixing time, which will be discussed further. The asynchronous sampling is unable to generate samples from true distribution and thus introduces a bias in sampling. In the above example, which runs on two threads, the state 00 should have no occurrence probability, which doesn't hold true for hog-wild Gibbs sampling. The mixing time is the amount of time it takes for the sampler to produce samples independent of its initial conditions, and is used for measuring the efficiency of Markov chain. Certain models run better and faster even in hog-wild Gibbs sampling. We deal with bias by finding type of those models. Total variation distance is too conservative as it depends on the difference over all the events in the sampling space, so the authors introduce sparse variation distance, which is least affected by asynchronous execution. This raised the question about the time required for running before the samples had low sparse variation distance from the target distribution. The authors define the same as sparse estimation time, which is bound within the context of a coupling argument using a parameter called the total influence. Such a distribution needs only O(n) samples and satisfies the Dobrushin's condition. We estimate mixing time of hog-wild Gibbs sampling for the same set of models. Mixing time is bound on distributions that satisfy the Dobrushin's condition. At coupling time, two Markov chains become equal regardless of their starting conditions. Union bound and quantity phi are introduced to bound the probability the chains are not equal at time instance t. We shall now see the contributions of the paper. Updates are modeled to serialize all writes, and delay parameters are introduced for representing how old a value the sampler is using. Total variation distance is calculated to find out how far the distribution is from true distribution. It is the maximum difference in probabilities assigned to a single event. The sparse variation distance rather estimates the maximum difference in probabilities assigned to an event with fixed dependent variables. Mixing time of the model satisfying Dobrushin's condition is bounded to be less than O(1) time extra as compared to sequential Gibbs sampling. Let us see how the authors propose the experiments. The experiment determines the effect of change in delay parameters on mixing time. The red line represents the mixing time that would be predicted by naively using the estimate of the sequential mixing time as a starting point. It is a very good match for the experimental results. This experiment shows that at least for one archetypal model, the theory accurately characterizes the behavior of hog-wild Gibbs sampling as the delay parameter tau is changed. Running hog-wild Gibbs sampling on a real-world on 11 GB knowledge-based population dataset against a multi-modal Gibbs sampler, that is, multiple threads with a single execution of Gibbs sampling running independently in each thread. The sampler will produce the same number of samples as hog-wild Gibbs, but will require more memory to store multiple copies of the model. Authors achieve speedups up to 2.8 times still around 8 threads. With more workers, the runtime of hog-wild Gibbs approaches multimodal Gibbs, indicating little effect on performance due to cache contention. Finally, we look at the results of the paper. For models that satisfy Dobrushin's condition, the mixing time bounds of sequential and hog-wild Gibbs sampling differ only by a factor of 1 plus O(n minus 1). For some class of models with bounded total influence, only O(n) sequential Gibbs samples are important for getting good marginal estimates. By using asynchronous execution, wall clock speedups of up to 2.8 times on real problems can be achieved. Here our presentation ends. If you liked and want to see more talks like ours, please visit scholar.stanford.edu. Thanks.